All right, let's talk about the hidden maps that run pretty much everything in our modern world. Graphs. You know, from your social media feed to the GPS that gets you home, graphs are the invisible webs connecting it all. And just to be clear, we're not talking about bar charts and line plots here. We're talking about these intricate networks of points and the lines that link them together.
So just imagine for a second you're looking at a map with a million cities, all connected by countless roads. The sheer scale of it is just overwhelming, right? Where do you even start? How do you make any sense of it? Well, that's exactly the challenge we're going to tackle. We're about to go on a journey to learn the essential tools for navigating and understanding these massive networks.
Okay, I know this looks super mathematical, and if you're coming from a world of neat tables with rows and columns, this might seem a little strange. But don't worry, it's actually way simpler than it looks. All this is saying is that a graph is made of two basic things: a bunch of points, we call them vertices or nodes, and a bunch of lines connecting those points, which we call edges. Think of it this way. V is all the cities on your map, and E is all the roads connecting them. That's really it. It's all about the relationships.
So we have our huge map. Where do we begin? Well, before we can do anything fancy like finding the fastest route or analyzing traffic patterns, we need to master a fundamental skill: just exploring the territory. We need a way to visit every single location without getting hopelessly lost.
And this is the core problem of what we call traversal. We need a strategy, right? A reliable method to visit every single node in the graph, exactly one time. Because if you just start wandering randomly, you could easily miss huge chunks of the network or end up just walking in circles forever. So, how do we do it systematically? Well, it turns out we have two main game plans for this. On one hand, you've got breadth first search, or BFS. I like to think of this as the cautious explorer. It starts at one point and checks all of its immediate neighbors. Then it checks all of their neighbors, spreading out layer by layer, really just like ripples in a pond. On the other hand, you've got depth first search, DFS. This is the adventurous explorer. It picks a path and just goes, diving as deep as it possibly can down one single branch before it ever backtracks to try another one.
Okay, so just exploring a map is great, but real-world networks often have rules. Think about one-way streets in a city, or maybe a project plan where you absolutely have to finish one task before you can start the next. Some paths only go in one direction.
And this brings us to a really special and important kind of graph, the directed acyclic graph, or DAG for short. Directed just means the edges have a direction, like a one-way street. And acyclic? That means there are absolutely no loops. Once you leave a point, there is no path that will ever bring you back to it. This structure is absolutely perfect for representing things with dependencies, like the steps in a recipe or all the tasks in a complex project.
So if your project is a DAG with all these dependencies, how do you figure out a valid order to get everything done? That's where topological sorting comes in. It's this incredible process that takes that complex, messy web of dependencies and flattens it into a single, straight-line to-do list. It guarantees that for any task, all of its prerequisites are taken care of first. It's the algorithm that brings order to workflow chaos.
So far, we've explored and we've navigated existing networks. Let's switch gears a bit. Instead of just using a network, what if we had to build one? Imagine you're in charge of designing the most efficient infrastructure you possibly can.
This is a classic optimization problem. Doesn't matter if you're laying fiber optic cables, building a railroad, or setting up a power grid, the goal is always the same: connect every single point, but do it with the minimum possible cost. You want total coverage with absolutely zero waste. And the solution to this problem is something called a minimum spanning tree. Let's just break that name down. It's a tree, which means it connects everything without any redundant loops or cycles. It spans the entire graph, so it reaches every single node, and it's minimum because the sum of all its edge weights, the total cost, is the absolute lowest it can be. It's basically the perfect skeleton network. So how do you actually build this skeleton? Well, one way is with Prim's algorithm. Think of this one like a really cautious builder. You start at any random point. Then, step by step, you look at all the possible connections to the outside, and you always pick the cheapest one to add next. It just slowly and steadily grows a single connected tree until every single node has been included. Kruskal's algorithm takes a completely different approach to the same problem. Instead of growing one tree, it starts by looking at the whole graph as a disconnected forest of individual points. It sorts every possible edge in the entire network, from cheapest to most expensive. Then it just starts adding the cheapest links, one by one, merging separate islands together as long as it doesn't create a cycle. It's less of a builder and more of a connector, just gradually uniting the whole forest into one single optimal tree.
All right, let's move on to a problem that pretty much all of us face constantly. You need to get from point A to point B, and you want to do it as fast as possible. Yep, this is the classic GPS problem, and it is all about graphs.
This question, it's right at the heart of every single navigation app on your phone. You've got a map with dozens, maybe hundreds of possible routes, each with different distances and traffic. How does your phone figure out that one optimal path in like half a second?
The key is that we're working with what's called a weighted graph. Not all paths are equal. So here, for example, the path from A to C is way shorter than from A to B, but maybe that path through C has a ton of traffic. The weight on an edge isn't just distance. It can be time, it can be cost, it can be anything we want to minimize. The shortest path might not actually be the one with the fewest miles.
The core logic humming away inside your GPS is Dijkstra's algorithm. It's this brilliant procedure that starts at your location and systematically calculates the shortest possible path to every other single node in the network. So by the time it's done, it hasn't just found the path to your destination, it's basically built a complete map of the quickest routes from where you started to everywhere else.
Okay, for our final section, let's shift our focus. We're going to take what we've learned about maps of roads and cities and apply it to maps of people. The very same principles that guide cars through a city can help us understand the complex dynamics of social networks.
See, by looking at a social network as a graph, we're not just seeing who's friends with who. We can look at the underlying structure, and we can start asking much bigger questions. Who are the key influencers? Where are the tight-knit communities? And how does information actually flow through this whole thing?
This kind of analysis starts with a friendship graph, where people are the nodes and their relationships are the edges. Within this big graph, we can find things like cliques. You can think of that as a small group of best friends where everybody knows everybody else. And then we can look for communities, which are bigger clusters of people who are really densely connected to each other, but have fewer connections to outside groups. Think about different departments in a company or different fan groups online. This helps us literally map the social fabric.
All this analysis of social connections leads to one of the most famous ideas in network science, and it can be boiled down to a single, powerful number: 6. It's the idea of 6 degrees of separation, the concept that you are connected to almost anyone else on the planet through a chain of a friend that is on average only about 6 steps long. It's incredible, and it shows just how small and interconnected our global social graph really is. Hey, if you enjoyed this journey through the world of graphs, do me a quick favor and hit that like button. Share this with someone who might find it interesting, and subscribe so you don't miss out on our next explainer. You know, from mapping territories to understanding society, these algorithms are just incredibly powerful tools. They give us a completely new lens to see the hidden structures that connect our world. So, the question I want to leave you with is this: what connections will you choose to explore?